Um, it is great to be here. It has been a great week. Party was wild and the trip one of a kind. So thank you, everyone. And I would also like to thank my co-authors here, one of which is here and two from home, for all of their work their help in getting this work done and submitted last week. So hopefully should be out soon if you'd like to know more. Now, why the South Pole? Well, this is where we are going, right? But the South Pole is also geologically and stratigraphically very complex and is also very old. But the question is, how old? And if there is ice inside PSRs, well, then how long has that ice been there for? Is it new ice? Is it old ice? Where is it coming from? But let's take one step back. If you wanted to know how old something is, then whether that being a plane, mare, an impact, a crater floor, you would be doing crater counting, and a lot of it. And that is what we did for about 40 planes at the lunar South Pole. Now, the panel on the left is the, in figure A, if you can see it, I'm sorry about that, is the hillshade map that we used for both the area maps and the crater counts. That is showing you 33 of these, both light planes and crater floors. And for those that don't know what a light plane is, these are all of these very smooth and flat plains that can be seen all over the moon. And of course, we've got them here at the South Pole too. In figure B, we then have the Amundsen crater floor, where we have additional 4 planes where we looked at smaller crater sizes compared to the Amundsen as a whole, labeled AM in figure A. And then in figure C, we have instead the L-Rock whack of the Schrodinger impact, where we have 4 more planes, 2 inner and 2 outer. And you might be able to spot, I hope, that we split these into 2 groups. Some are blue and some are red. So the blue ones are those that we could date with the PF and CF of Neuquén 1983, but even with the updated one, 2001, it's the same age, so no difference there. And the red ones are those that we could not date. And that is because most of the crater size range would be on the Trask line, where the number of craters that you form is the same as the number of craters that you've lost. So whatever age you would try to fit, that plane or crater floor would be older, okay? So what did we find? After many months and many crater counts by hand, we find that these planes split into 4 groups, and these not only share a similar age, but they're also geographically close to each other, okay? So if we start from the oldest group, and that is the 3.8 planes, well, of this group are part the Schrodinger planes, which is not new. We knew this from older work from Orgel, if she was here, and Vade Bogert, that is at home. But what we did find is that this older age extends all the way inside Amundsen crater floor as well. The next group is the 3.7s, and these are planes found outside of the rims of Amundsen crater and for the Shoemaker crater floor. We then find a smaller group of planes outside of the rims of Shackleton that date in the 2.5 billion years. We then have 2 planes that are somewhat outliers. After a closer look several times, we found, but you can't see them here, sorry. There are some very fresh and sharp craters near these planes. So we think that probably those fresh craters are resetting those ages to these 2 3.67 and 3.9 that don't quite fit in all the other groups. And then what about the other two PSARs, Howarth and Faustini floors? Well, we couldn't date these either as well, but we did not even turn them red. And I will show you why in about 4 slides. But first, I would like to get more into the data of each of these groups, showing you some CSFD plots where we get our ages from. Now, here I am showing you the CSFD-R plot, which is on a log scale, which basically gets rid of the -2 and -3 slope of the cumulative and the differential when it comes to dating. So that is why it's flat. And what you are seeing is a series of squares, and my crater counts would be contained in these bins by crater size range. Okay. And what you can see is that the age that we fit in these bins is pretty much the same in all of these planes. So we have a very consistent 3.8 age for the same crater sizes. Okay. And I forgot to mention, because these are very likely the same ages, it means that they formed at the same time. And if they formed at the same time, then they very likely share the same source, which we think it's the Schrodinger impact itself. Now, these are the 3.7 group planes, which I did not include the Shoemaker because it goes in the next slides that you will see soon. Now, in this case, we have very similar plots. So we have a very consistent 3.7 age for the craters, the same crater size range. But in this case, the sourcing was a little more complicated because there are no basins at the South Pole that are 3.7, nor there are large craters that are close enough and big enough to have formed all of these. And so in these cases, you have to look at a more of a bigger picture. And so what we think is going on, where are these planes coming from, are the far side Orientali basin. Now, that is not unlikely because there are older studies and some new counts on the rims of the basin that has this same age. But also on a wider study of light planes on the moon that we also did, that is coming out soon too. We find that the far side planes also most date in the 3.7. So it is normal to imply that these southern planes also must come from the same group. Okay. Now, finally, we get to the slide that I promised. So here oh no, this is Shackleton, right? Okay. So for the Shackleton planes, it's the same story, right? Same fit for the same crater size. And why we think these planes are dating the Shackleton impact itself mostly comes from one area, and that is Shackleton 4. This one, as you can see it in the little square there, is that it is very close to the rim. And yet it has a very consistent age with all the other planes that we have close by, okay? Which it is younger than currently known, but we are pretty confident that we are hitting the impact here. So here we have it. Now, these are the 3 crater floors that many people are interested in. As I said, Shoemaker crater floor dates pretty well with a 3.7 age, but we couldn't quite do so for the other 2. Now, and that is because most of the crater size range is sharp on the Trask line. So you cannot get an accurate age in that case. You could try and date your largest bins, but clearly the age of that crater would be, of that crater floor would be older, okay? But what it is clear that is going on here, and you cannot see it here. I hope that you can on the smaller screens. We did fit a 3.7 billion year age isochron on these two floors, which clearly shows that something did happen at this point that didn't quite reset these floors completely. So we are having some sort of partial resurfacing where the largest craters have not been covered. Okay, so these floors too, if you would try to fit them, they would be older. I have to rush through here. Now, if I put all of these planes up into one simple graph and sort them by age, you can clearly see the four different groups with their era bars. But then you might say, hold on. Some of the era bars of some planes in the 3.7 groups overlap with some of the planes in the 3.8. So aren't they all the same age? Not quite, because these are not cumulative eras where the age can be anywhere on that line, but rather these are probability plots, which come from Michael et al. 2016 that you cannot even read there. Where the age that I showed you is the most likely. So anywhere that you move on that line, it would be less and less likely. Okay. So then the next question was, well, how do we prove that? Well, one thing that you can do is you can take those error bars for any plane and put them in a smaller plot over age and compare where the gray area is. It's supposed to be gray, where the median line is your most likely age, and the area under that curve is your era. So if your eras overlap, then you are looking at the same age. But if they don't, they are two separate planes. And that is what we did. We took Schrodinger M1 and Amundsen floor as a whole. We compared those era bars, and they clearly do overlap. So it is true that we are looking at the same planes that formed at the same time, while we can, but neither of these two overlap with the Shoemaker crater floor for the 3.7 billion year group. So we are definitely looking at two separate groups that happen probably very close in time. So it is very difficult to differentiate them, but with this way, I hope I've convinced you that they are separate. So this is my last slide to sum up what we found. And if I can make one last point, it is clear that at the South Pole, light planes can form as stacks or layers from multiple impacts, but also small craters can form light planes, which is most likely or very likely possible also on other parts of the moon, rather than them being formed all as a giant impact. Thank you.
Thank you. We have time for a couple of questions.
We're all hungry.
Yeah. So I have one quick question. Maybe I missed it, but is there also any like evidence in the images whether you could see some superposition relationship between those units anywhere, like to do some relative stratigraphy just to cross check?
Yeah, so, well, we didn't look into that. So the mapping of the areas come from a visual flat, right?
Okay.
So you would look for flat and smooth planes. But we didn't do any, or we didn't look at any other map to see what's going on, even because if there was something on top on the CSFD plots, that would come up. Okay. In the case of the red plains, or those where we are seeing partial resurfacing, then something else is going on there, right? But we didn't look further into that, because the point of this work was to date as many planes as we could, to give other people as many dates as we could, right? But it is also true that for the areas in red and those where the entire crater range is on the Trask line, that you can't date those because there is so much that happened, and the craters, you can no longer track if it's in production or not. So yeah, that's why it's best not to date those parts.
Ah, we have one question there.
I'm not giving you the lunar tartan.
You showed a good mathematical argument for why your two older units are different ages, but do you find any stratigraphic relationships or cross-cutting relationships that would also give further support that the two are separate in age?
Yeah, that is a good question. So the areas for the 3.7s and the 3.8s, they are apart. They're separated geographically too. So they're not close to each other. It's the areas within each group that they are close. However, and this I have not said, so I can say it now because you've asked. Light plane 6, which is an area between the Amundsen and the Schrödinger over the big flat plane in the middle. Now that one, that plane also dates in the 3.8. However, geomorphologically, it is a little contradicting because it does look to superpose everything else. So why is it so old? That is an unanswered question, but yeah, thanks.